we want to lift an object up from height A to height B. Some distance h. And first, I'm just going to lift it straight up from A to B. Here's our initial spot, and we're just going to lift it straight up, and that's our final spot. And we want to say the work done, we'll call this 1. The work done on path 1 is going to be by gravity, right? Work done on our object by gravity and going from A to B. So it's the force of gravity times the distance times the cosine of the angle between them, right? Minus mgh. We good with that? That's straightforward, right? Now, I'm going to take a different path. Call this path 2. I'm going to lift it up to here, and then I'm going to bring it back down to there. And this is going to be, what do we call that? C. And it's going to end up right there. So the work done for path 2 is going to be, let's break it up. Should we do 3 sections? First, we'll go to there. Then we'll bring up beyond. And then we'll have a third section where we bring it back. What do you think the work is going to be? So we get, for section 1, mgh cosine 180 degrees, right? That's our first section. We add to that the work done on our second section, right? Because the first section is identical to what we just did, right? Now we're going up some more, right? So we're going to get mgc cosine 180, right? That's our second section. Now we're going to add the work done by the third section. It's going to be mgc cosine of what? So on our second section, we're going up, but the force of gravity is down. So we get a cosine of 180. In our third section, we're going down, and the force of gravity is down. We get a cosine 0. Right? In the second section, the force of gravity is doing negative work. It's slowing our object down. On the third section, the force of gravity is doing positive work. It would be speeding it back up again. We see that? So let's see, the work done by gravity over this whole thing is going to be negative mgh, negative mgc, positive mgc, negative mgh. What do you think would happen if I took this path? What do you think would happen if I took this path? You could answer me already. It doesn't matter what path I draw there. I'll start with an easy one. Right, first down and then up. It's going to be the same as going up and then down, right? How about this path? It turns out they're all the same, right? The work done on path 1, the work done on path 2, the work done on path 3, the work done on path 4. work done on any path between A and B is going to be the same. And this is a special kind of force. Whenever this happens, whenever the work done is independent of the path taken between the 2 points, it's a special kind of force. We call it a conservative force. So this means that this is a conservative force. And whenever we have a conservative force, what do? We say, you know what? Why deal with work done? It's independent of the path. Let's come up with another quantity that only depends on the endpoints. So let's figure out what the work is by gravity. In this case, we know it, right? It's mgh. The work done by gravity is mgh. And so let's say that that is going to equal, we always say the change in potential energy. We're going to come up with another term. Instead of using work, we're going to come up with another term that only depends on the endpoints, only depends on position. So mgh only depends on position, right? The height in the gravitational field. So we're going to say work is negative the change in potential energy. We use U for potential energy. Work equals negative change in potential energy. When do we come up with the potential energy term? Anytime we have a conservative force. So the first conservative force we know about, gravity, we're going to come up with a potential energy term for gravity. Yes. So our gravitational potential energy is going to equal mgh. And it's a type of energy. They use mgy in the mgy, a position in the gravitational field. And we don't really care. All that's important here is changes in potential energy. To say something has a certain amount of potential energy is not that meaningful. But to say its potential energy changed from A to B, then that tells us something. We can use that information. So the Y is kind of arbitrary. In other words, if I wanted to use potential energy to figure out how fast this thing's moving when it hits the desk, I'm going to let go of this, right? And it's going to hit the desk. And I want to figure out how fast it's moving before it hits the desk. Maybe I said the desk is 0 height, and it starts out, 1 meter above that. And I can figure out the potential energy it has and how fast it's moving when it hits the desk. Maybe you said the floor is 0 height, and it starts out at 2 meters. But where does it end up? For you, 1 meter. For me, it ends up at 0. So we both have the same change in height. We both say it started 1 meter above where it ended. And when we figure out our potential energies, we're both going to end up with the same answer for the change in potential energy and how fast it's going when it hits the table. So it's the 0 reference is kind of arbitrary. What's really important is changes in potential energy. So there's our potential energy term for gravitational field. This only, of course, works when the gravitational force is constant, when it's mg. When is the gravitational force equal to mg? When you're at the surface of the Earth, okay? And you're not moving very far. If you start to move far away from the surface of the Earth, it drops off as you move away, right? And so it changes. So when we deal with, in a later chapter, we're going to deal with satellites going around the Earth, or the moon and the Earth, things like that. We don't use this anymore for our gravitational potential energy. We have to come up with a different term. But as long as we're moving near the surface of the Earth, this works for gravitational potential energy.